Excellent. Hi everyone, so today I'm going to tell you about the cosmological constant, or what Albert Einstein called the greatest blunder of his scientific career. So to begin with, we're going to go back roughly 100 years to the beginning of the 20th century, where most astronomers thought that our universe consisted of this: our own Milky Way galaxy of stars and gas and dust, and that's it. There were these funny blobby nebulae things that we didn't quite understand, but fundamentally, scientists thought that our universe consisted of just our galaxy. They also thought that our universe was static, or unchanging with time. So that means that scientists back then believed that if they could get in a time machine and go back 100 years, that 100 billion years or something massive, the universe would still fundamentally look the same. Or equivalently, if they could get in a time machine and go forward 100 billion years, the universe would still fundamentally look the same. Now this worried old Albert Einstein, because he'd been doing a lot of thinking about gravity between 1910 to 1920, and he realised that if our universe did just consist of stars and gas and dust, the gravitational pull between everything would make it all collapse in on itself. But Einstein thought that we lived in a static universe. So he said that there must be some other force opposing gravity to stop the universe from collapsing back in on itself. And he called this the cosmological constant and gave it the Greek letter lambda. So there was a problem with this theory that didn't worry old Albert, in that it's actually an unstable solution. It's a bit like trying to balance a pen on its nib. You know in theory that you should be able to do it, but little tiny variations just send it falling over. But as I said, that didn't worry old Albert. What did worry him was this chap, Edwin Hubble. So Edwin Hubble looked out at those funny blobby nebula things and realised that actually most of them were whole other galaxies. So in an instant, the size of our known universe ballooned. It went from being one galaxy, ours, to hundreds of things. And Hubble also realised that the galaxies are all moving away from us. So this is a plot from his famous 1929 paper. And it basically tells you what some of those galaxies are doing. So on the x-axis across the bottom is how far away galaxies are from us. And on the y-axis is how quickly the galaxies are moving away from us. So as you can see, as you get further away, as galaxies get further and further away, they're moving away from us faster and faster. Now this is a telltale signature of an expanding universe, not a static one. So Hubble realised we live in an expanding universe. If you play an expanding universe backwards, you might expect originally everything to have started off at the same place. So this led to the idea of a Big Bang. So scientists then thought that our universe, the history of our universe, was that there was some initial injection of energy right at the beginning, which caused the expansion of the universe outwards. And over time, through gravitational interactions between all the galaxies, that rate of expansion will have slowed down. So that was our new model of the universe, one that doesn't need a cosmological constant. It's not static. So this is what Einstein called the greatest blunder of his scientific career. Because if he hadn't so doggedly believed that we lived in a static universe and put in this cosmological constant, he could have perhaps predicted that we live in an expanding universe, and maybe even that the universe started in a Big Bang. So that was the way it was for decades. After Einstein's death, astronomers thought that the cosmological constant was a mistake. That was until about 1998, where scientists started to understand what was going on with these really cool types of exploding star. So there's a type of exploding star called a type 1a supernova. And actually for it to happen, you need two stars. You need one giant star and then a much smaller white dwarf orbiting around it. So a white dwarf is just a star with about the mass of our own sun, but squished down to about the size of the Earth. So here we have a little animation to show you what goes on. So here we have the white dwarf at the bottom left at the moment, orbiting around the giant star. And as it goes around, you see it's actually stealing mass from its giant companion. There's a stream of gas going from the big star to the white dwarf. So the white dwarf accretes this matter onto itself and gets heavier and heavier until it reaches something called the Chandrasekhar mass limit, and then it explodes in a thermonuclear explosion. So when these things go, they are some of the brightest things that we can see, which is handy because it means we can see them really far away. So this picture here, this is a nearby galaxy, and this dot just there, that is a star. That's in that galaxy, a white dwarf, something the size of our Earth, exploding. So it's really bright, you can see it really far away. There's also this really useful relationship between how long the explosions take to happen and how intrinsically bright they are. Which means that if we watch one of these things go, time it, figure out how intrinsically bright it is, we can figure out how far away it is. It's a bit like if you took a car and plonked it right in front of me and turned the headlights on, I'd be dazzled and blinded. I could tell that the car is very close because it looks so bright. However, if you took that same car and put it on a nearby hilltop, turned the headlights on and shone them at me, I wouldn't be dazzled or blinded. I could tell that the car's far away because it doesn't look so bright. So this is what we do. If we can figure out how intrinsically bright one of these type 1a supernova is, compare it to how bright it looks, we can figure out how far away it is. Because they're so bright, we can see them very far away, we can extend out Hubble's graph from earlier, the one that showed the universe was expanding. And we found something very interesting. Scientists found that actually, the rate of expansion of our universe wasn't slowing down like we predicted it should, it's actually speeding up. So gravity isn't slowing down the expansion of our universe. So once again, we needed some new force counteracting gravity. We needed a cosmological constant. So originally Einstein put this in to make the universe static. We're now putting it back in, not to make the universe static, but to speed up its rate of expansion. So do we know anything about this cosmological constant, other than a name, and we've given it the Greek letter lambda? Well, we have a second name for it. The second name that we can also give this is dark energy. And it's this dark energy that we believe is driving the expansion of our universe. But before we can get into any detail of what dark energy is, we first need to have a think about normal matter. So normal matter is things like you and me and this lecture theatre and the Earth and the Sun, or a paperclip. So we're going to do a little thought experiment. So if I take a paperclip and put it in a meter-cubed box, my density of paperclips is 1 paperclip per cubic metre. But if my universe is expanding and my box gets dragged out to 2 cubic metres, my density of paperclips has dropped. And I only have 1 paperclip per 2 cubic metres, or half a paperclip per cubic metre. So over time, with the expansion of the universe, the density of matter will drop. What happens with dark energy? So if I put some dark energy, a blob of dark energy, into a box, let my universe expand a bit, the density of dark energy doesn't change. This means over time, as the density of normal matter falls, normal matter becomes less and less important, but dark energy becomes more and more important. So I suppose a legitimate question might be, how much dark energy is there in the universe? Well, these are some pictures of the telescopes I work on, one in California and one in South Africa. And sort of a spin-off of what we do will be that we'll be able to better constrain how much matter and dark energy there is in the universe. But our current best guess is that there's about 30% of our universe is made up of matter, and the other 70% of the universe is made up of this dark energy. So we live in a dark energy-dominated universe today. So this is ultimately going to determine how our universe ends. So here is a picture of the Hubble Extreme Deep Field. So this is just a photo, really deep into space. And I've basically just put it to show you that right now our universe is full of lots of cool, interesting things which you go out and study, like galaxies and stars and planets. But if you could go forwards several hundred billion years, what might the universe look like? If I could take this photo again, I might get something that look like that. So what's happened here? So over time, as the universe expands, normal matter, gravity, becomes less and less important. Dark energy starts to dominate, and the expansion rate of the universe will speed up, until eventually, if I'm stood in one galaxy, the next will be moved so far away from me that I won't be able to see it. And then after that, after a few more years, even the very galaxies themselves will just be torn apart. And ultimately, the atoms that make everything up will be torn apart by dark energy in a big rip. So this dark energy, this cosmological constant that is ultimately going to determine how our universe ends. And that was Albert Einstein's greatest blunder. Thank you very much for listening.